Hello viewers, and welcome to the flagship series of this channel. 7 Sins of Robotics aims to detail the 7 most common and destructive mistakes that roboticists make in the design process. It is my hope that by making clear where all the easily avoidable pitfalls are, aspiring engineers watching this may fare far better than those who came before. First things first, we need to set some rules so you understand why I've organised this series in the way that I have. Firstly, all of these sins are born from my personal experience and observations of failed robotics projects going back nearly 2 decades. Obviously, other roboticists may disagree with what is included or object to the order in which they are placed. Everything is subjective after all. Anyone attempting robotics will quickly discover that all robots are unique to one another. No 2 robot designs are alike. No 2 development cycles proceed quite the same way. As such, in order for this series to make any form of logical sense, we must gather specific blunders into general categories that apply to many projects, and not simply detail various errors that could or could not occur in your project. Because of this, the titles of these categories may not make sense to you until you dive deeper and actually see what I have put under each category. All of the sins will be listed in order of severity to project integrity and their time of appearance within the project. What this means is that a moderate sin that occurs at the beginning of a project will be listed before a more severe sin that occurs at the end of the project. And of course, if you're simply doing robotics for the fun of it, none of this is really going to matter. After all, these errors that I'm listing only matter if you're planning to sell your robot to an investor or straight to the paying public. So we finally arrive at our first sin, failing in concept. Yes, it is very possible to fail your robotics project before you even put solder to iron. Any form of commercial project, not necessarily just a robotics project, is weighed down from the beginning by a list of constraints that must be adhered to. Failure to manage said constraints invites disaster, but before we get there, we must first understand what might limit your project. Because they will be the ones funding your project, the wishes of the investors will always be a massively important aspect. This can cut both ways, because although they can provide needed oversight, they are often unfamiliar with the quirks that come from robotics engineering. This very often leads to some spectacularly poor decisions which can compromise your project from the very beginning. An example of this might be the mandated use of certain unsuitable materials for the chassis to save time or money. Roboticists are constrained by the limits of the technology at hand. This is not necessarily the limits of technology that humanity has invented, merely that what you can afford with the money that you have on hand. Everyone wishes to have their own robot butler, but you may not have the components or the knowledge in order to bring this design forth into reality. Failure to bear these limitations in mind will always lead to disaster as your design bumps up against the hard limits of reality. A vitally important, yet often underestimated aspect of robotics design is the style of the engineer themselves. Robotics is as much an art form as it is an engineering exercise, and like art, it can often be massively misunderstood by those who do not understand the thought processes behind it. An excellent example of this is designing a walking robot's leg. Unless the replacement engineer understands exactly what the designer was thinking when he created it, any modifications he creates will barely function, if they work at all. Bearing this in mind, if the project you dream of needs some form of modularity or later modification, you must take great pains to hire an engineer who does not have an esoteric design method, or build a robot which does not have complex components. This can be much more difficult than you might expect. Finally, obviously, your project will be limited by where the robot must operate. If the robot is an airborne drone, you must watch its weight. If the robot must operate in a swamp, wheels will be ineffective. If the robot must operate in a classroom with children, it must be safe to handle. This may seem obvious to most, yet a lot of roboticists often neglect this to their cost. So, bearing all that in mind, where do we start going wrong? In the initial stages of the robot's design, it is far from uncommon that oversight will be lacking. Many roboticists, not necessarily rookie roboticists, hold the opinion that any deficiencies caused by lack of clear vision in the beginning can be remedied later on. While this may or may not be true in general engineering projects, it is always fatal for a robotics project. The designer and the investor must be very clear from the beginning what they desire, otherwise the project will disappear into development hell and wasted funds. Speaking of, many first-time investors will often underestimate exactly how much money it takes to build their robot. These costs are consumed by the varying electrical, mechanical, and software failures that plague robotics projects. What's even more irritating is that these failures are often unavoidable. Remember, with robotics you are pushing out the bleeding edge, and no one will have encountered your problems before. So, when finalizing planning, you must budget for these potential failures, or else see your project costs spiral beyond that which was initially agreed. A rapidly and unexpectedly increasing budget will, obviously, put immense strain on the relationship between the designer and the investor. Compounding this is the drastic underestimation of how long it takes to bring a project from the design board to a working prototype, then to a finished product. In my experience, if you are starting a project from nothing, then it will require a design cycle of at least 5 years, and that is if everything goes perfectly. Now, because nothing in a project like this ever goes perfectly, the roboticist and the investor must understand the commitment that any robotics project requires. The length of time said project requires, along with the strain on the finances, is one of the most common causes of death for aspiring robots. Compounding everything previous, the roboticist must take into account the varying fragilities of the robotics project they're working on. To put it in simple terms, if an engineering project is like an American football player, then a robotics project is said player with brittle bones. The bumps and scrapes that would normally only inconvenience the project will cause the robotics project's demise. Both investor and designer must bear in mind that large problems in a robotics project are very common, and that it is how quickly and how well these problems are solved that determine the overall health of the project at large. Any project where problems keep mounting up, or where existing problems breed new ones, are generally destined for failure. Now, more mundanely, a bad choice of components can sabotage a promising robot from the very beginning. I should make it clear here, the components that you choose are not necessarily rubbish to begin with, they can be reliable and easy to use. However, components that have consistent results in isolation will often behave very differently when placed upon the moving chassis of the robot, and these little quirks of the equipment will often, lead to catastrophe as the robot behaves in an unexpected way. Any aspiring roboticist must conduct extensive tests on how his components behave before committing to the full project. In the glory of designing one's own special robot, it is depressingly common that the roboticist will often overlook who this robot is meant to be for. Designer inexperience can cause this problem from the beginning. However, this is not the only cause. One major quirk of robotics projects is that, when a serious fault occurs, the robot will often need to go back to the design phase in order for the problem to be eliminated. This means that mistakes that are only normally possible to make at the beginning of a project can reoccur later on. The robotics engineer must make sure that when these redesigns occur, the robot's design does not deviate from the customer's needs. But what are these needs? Obviously, the attitudes of the target demographic are vital. If the customers are not willing to pay for robots because they find them offensive for reasons religious, moral, or practical, then the project is a non-starter. These situations generally occur because the designer or investor has a personal stake in the robot and cannot countenance its rejection. The roboticist must always adopt an emotionally detached perspective when analyzing his project, or money, time, and reputation is wasted needlessly. Another common failing is that the robot will be priced beyond the capacity of the customer to pay for it. It is stupidly common to see that few working robots be priced in the range of tens of thousands of pounds, or dollars depending on which side of the Atlantic you're on. To put this into perspective, you could pay for a good car for the price that they're asking for these robots. The designer must therefore ensure that the customer is receiving a worthwhile product for the amount of money that they will likely have to shell out. Anyone who's watched any robot advertisements online will understand that this is rarer than it really should be. And finally, we must bear in mind the choice of style of the consumer. Unlike the choice of style of the designer, which will often be seen in the mechanics of the robot, the choice of style of the consumer must be borne in mind in the superficial design. What does this mean for the everyday person? Well, the customer is unlikely to pay a 5-figure sum for a robot clad in cheap plastic. This is, again, far more common than it should be, and it is an easily remedied issue. How does said robot benefit its end user? This is a question that is so often unheard in design sessions, and yet it is incredibly important. Many purchases of a device will often occur because someone will idly notice the benefits that the robot will bring and reason that the price they will pay for the robot is worth its utility to them. Many roboticists neglect this out of pride in their big idea, only for their project to collapse into ignominy and obscurity. So how can a robot bring benefits to its user? Well, the most obvious use for a robot is as a time-saving device. After all, why would you have to spend time hoovering when you could simply get a robot to do it for you? In these situations, the roboticist must bear in mind that the time saved by the robot doing the job that a human would otherwise have to will have to be balanced against the robot's maintenance and malfunction handling. The end user does not want to sink more time into keeping the thing running than if they'd simply done the job themselves in the first place. Perhaps the most useful benefit that robots bring is in the mitigation of risk to the health of the end user. This benefit will often be seen in industries where the robot will take over the operation of a machine in a potentially dangerous situation or location. The roboticist must ensure that the robot can perform the task to standard and can be easily retrieved if it malfunctions. Many of these robot projects fail because the robot malfunctions and the user is put in more danger trying to retrieve it than they would have been simply doing the job. An often overlooked benefit to robotics is in comfort and leisure. A ball-throwing device is a robot, albeit a very simple one, yet they are used ubiquitously by sportsmen attempting to hone their skills. When designing a robot in this genre, the engineer must liaise closely with the end user because their needs will be very specific, and any deviation will result in unwanted behavior from the robot and the failure of the project. Perhaps the most important use for robotics, however, and the most neglected, is in education. Many devices we use these days possess some form of limited autonomy, classifying them as robots, and yet many people have no idea how these devices work. It is incumbent upon roboticists that exist now to introduce devices that inform and teach school children the concepts they need to understand to build robots and maintain them. Yet, any such devices that have been attempted in the past have been badly managed at best, resulting in malfunctioning abominations that only serve to deter people from exploring the subject. Of all the problem areas mentioned, this is the one most in need of addressing by the robotics community. Well, that was an awful lot of exposition. So how does this actually apply in reality? Well, in order to help you visualize all of this, there are two relevant archetypes of this sin that can occur. The very first of these is the crime of chasing the dream. Now, the root cause of this is usually some form of fad that has taken root within society and that people can make money off of it. Now, if you've been paying attention so far, then you would know that robotics projects take a very long time to complete. Because of this, taking advantage of these passing fashions is going to be an incredibly large ask. People are fickle creatures, and what is fashionable one year will not be the next. As a result, This mistake is usually made by project leads who do not have a great amount of experience with robotics, in particular the extreme length of the project timeline. Underestimation of the amount of time it takes to bring a project to completion will lead to the robot releasing to the public long after it has become culturally irrelevant. The effect this has on the company, the investors, and the designer is simple and stark. Because of the obviously badly conceived, very dated vision, and the waste of time and money, everyone involved will suffer an irrevocable loss of reputation. This is vital, as an engineering company's reputation is by far its most important asset. Think of the hit Tesla took with the failure of the Cybertruck. So how do we avoid this ignominious failure? The aspiring designer must bear in mind the length of time for the project's completion. And again, I'm quoting 5 years minimum here, but it will probably take longer than that. As such, any project that needs to take less time than this will assuredly fail from time constraints. Now, one important exception to this is projects that will make minimal changes to a robot's design. For example, changing the coating of a robot from plastic to aluminium is unlikely to throw off anything major in the robot's design and, with luck, may be completed on a short time schedule. It is important for you to know that the robot will be accepted when it finally goes to market. If you have any uncertainties as to whether this is going to be the case, then you should engage a good marketing team or do market research yourself. This ensures that your product is viable before you try to spend any money on it. If the market team comes back saying that the fate of your product is uncertain, think very carefully if you wish to commit to it. If this is your first time attempting a robotics project, and there's a lot of money on the hook, it's best to contract some experienced roboticists to provide advice. If there's someone out there who has tried something similar to what you're doing, they may be able to give you good advice on how to avoid any problems before they become an issue. Now, let's explore an example of a robot where this failure has occurred. In front of you now is a picture of what is, imaginatively, named the two-wheeled balancing robot. It is programmable, utilizing either a wired or wireless connection via the Arduino programming framework. For those viewers who are unfamiliar what Arduino is, it is an open source microchip programming framework and language meant to be accessible to beginners. So already we can see that this robot is meant to be targeted towards an educational audience, and coupled with the fact that the robot comes to around £61 at the time of recording, it is meant to be financially accessible to the average individual. Now at this point, I'm going to blow up the picture for us to get a closer look at this robot, because it's when you take a firm look at the various components of this robot that the problems begin to surface. Our first port of call is the sensor mounted on the front of the robot. This is an ultrasonic distance sensor meant to prevent the robot from crashing into anything in front of it. Its model is very common, reliable, and can easily be bought online from any number of stores. Moving downwards, we can see a pair of electric motors mounted on brackets attached to the main chassis of the robot. These motors and brackets are also standard components and again can be bought easily from any number of places. By this point you should be noticing a trend, which continues with the third component. This is a small LCD display meant to inform the user what the robot is doing, and again this component is readily available from any internet store. However, considering most LCD displays of this type are touchscreens, it is notable that this monitor is not, due to it being mounted beneath a perspex panel. An obvious opportunity missed for a user input device. Coming back to topic, the only component on this robot that is not off the shelf is its printed circuit board, and the only reason they've done this much, I believe, is to minimize costs by combining multiple components into one large board for ease of manufacture. Clearly, minimum possible effort has been made in construction, and the robot is about to be punished for this. So given all of this information, where did the designers go wrong here? Well, the crux of the problem lies in one final piece of information. This is a kit robot. Anyone who buys this must assemble the components themselves into the complete product. Because of this, Only hobbyists and enthusiasts are likely to buy the robot at all, and this is the point where everything falls apart. Because this robot is made almost entirely from off-the-shelf components, any hobbyist is likely to simply buy components themselves rather than get it from this manufacturer. Not only is this cheaper than buying the complete robot kit, but by doing this, they are able to use components that they are personally familiar with and are happy using. This method also has the added advantage of the end user being able to modify the robot to their benefit, and therefore better provide for their needs. And so, what should be a simple, cheap robot that is easily accessible to the market at large is in fact so simple that any prospective customer will simply produce it themselves. This fact is only really noticeable when you take a deep dive into what's going to happen when the end user takes charge of the robot. This should have been discovered during the planning stages when someone asked the question, how does this benefit the end user? But because planning wasn't well thought through, robots like this one make it to market with mixed results. A final point to be made here is that there are more problems with this design than just what I have stated, but because they are not relevant to this particular topic, we'll save them for another time. And now we move on to the second major archetype of this sin, when someone self-important stands up in a meeting and asks that fateful question, why can't we just do this with the robot? Any engineer you speak to will have horror stories that start with precisely this setup, but roboticists are the only people who are pretty much guaranteed a bad ending. Any intervention in a complex, unforgiving subject by someone unfamiliar is almost guaranteed to be a disaster. While it is possible to ignore stupid suggestions from within the project team, it is far more difficult to field unreasonable demands when they come from the project superiors. Said superiors are meant to give oversight, and suggestions can be made with the best of intentions. However, when these suggestions are not properly thought through, the end result is always the same. Less common than the above, but arguably much more destructive, is when the world just leaves your project behind. This can take many forms, but the two most common are, because of that long development cycle, the robot can end up being obsolete by the time of its completion, and, due to changing national economic factors, the robot may no longer be a viable product. When this happens, people inevitably start looking for ways to salvage the project and make some money back. These plans tend to be ill-conceived and fall victim to the sunk cost fallacy, throwing good money after bad. The effects of all of this are quite simple. Any badly thought out modification to a project can ruin a promising robot and turn well invested money into a waste. Engineers will also waste a lot of time trying to make work modifications that they knew were bad to begin with, again wasting more money. Fortunately for the aspiring roboticist, all of the above is simple to avoid. As with all things, having proper oversight of a project can stop many problems before they begin. In order for this to be successful, communication between the investors and the engineers must be clear and without acrimony. Both the investors and the roboticists have a large personal stake in the project, and therefore any modifications must be scrutinized carefully and be viewed impersonally. With regards to world affairs, the best defense in this case is to do proper research and to effectively keep one eye on the future. Innovations of the past may give you insights into what happens next, and it is well worth keeping an eye on the financial markets and business opportunities. This ensures your design is up to date with the current market economy and insulated against rapid change. But what if you can't predict the future? In this case, it is important to plan this uncertainty into the first design of your robot. If you are unsure whether a particular component will be there in the long run, then plan obsolescence and modularity into the design. This will bump up costs, so it should not be used as a catch-all and instead as a required safety net. However, in cases where there is uncertainty, modularity will save you from a much greater cost later on as the design fails. The devil of it is, this mistake is easy to avoid, and yet so many robot projects fall victim to it, even some quite high-profile ones. What we have here is a picture of perhaps the most famous robot that has ever been built. Boston Dynamics' Spot robot dog is the poster child of a successful robot. It was designed as a technical demonstrator for a particular type of unstable leg. Now, what this means for the layman is that it was never meant to be a commercial product. Instead, it was simply built in order to see whether a particular engineering challenge could be overcome. Now, when I say unstable leg, this is instability in the technical sense, not in the pejorative sense. Just because a design is unstable does not necessarily mean that it is bad. For example, modern jet fighters are aerodynamically unstable, and this allows them extreme maneuverability. The instability is controlled by computers on board the jet, which counteract the otherwise uncontrollable motions. Similarly, the legs on this robot are designed in order to take advantage of said instability in order to greatly enhance the ability of the robot to move. Of course, most of the time of development was spent overcoming the otherwise unwanted unstable motions. The development cycle was a success, and the robot continues to be advanced in terms of its capacity to move in different environments. So if all of this sounds great, why is this robot on the list? Well, whenever any successful product is designed, inevitably there are people who try to modify it to their own ends. In these pictures here, we can see the original design as well as two copycats, one meant for the military, the other meant for domestic delivery. But at this point we must ask the question, why was this done? At the time the robot was technically successful, there was significant interest from third parties to try and make the robot a successful commercial product. Many people ask the question, why can't we make this robot do this job? The fact that you don't see these robots ubiquitously despite its completion demonstrates how successful these modifications really were. Many commercial jobs require the device in question to be stable in order to carry delicate or expensive objects. Utilizing a design with an unstable leg was already going to be a bad decision. Coupled with this, the many modifications that had to be done to make the design successful have made the robot extremely complex and therefore expensive to build and maintain. Any sort of industrial or commercial job requires the robot to be independent and reliable. After all, if they wanted complaints, they could just get a human to do the job. Speaking of humans, an often underestimated aspect of putting a man into a job is their ability to creatively work around problems that occur on a day-to-day basis. In order for a robot to have similar potential, it must be modified in order to take advantage of these openings. If you can recall back to the beginning of this video, we talked about how redesigning a robot's leg can be an extremely arduous task. Because of this, being able to rapidly or extensively modify this robot in order to meet different demands was always going to be difficult if not impossible. And this, ladies and gentlemen, is how a successful product can be turned into a useless failure by one simple question. Now, before we wrap up this video, I thought I might preempt some obvious complaints that you might have upon watching this. First things first, yes, I am well aware that most business people will have already experienced the brutality of a failed product in concept. My point is not that this failing is unique to robotics, far from it. Instead, my point is that robotics is particularly susceptible to this death, and therefore the danger areas should be handled with consummate care and attention. Others might say, if individuals are the problem, can't you fire them and get better employees? Of course this is possible, unless the problem makers are your superiors/investors. Even if the problem emanates from one of your subordinates, if their contributions are irreplaceable, removing them is not feasible. This solution should not be used without due care and attention. Finally, of course, if the design is bad, why not change it? Well, the inevitable consequences of this course of action will be the contents of my next video in this series. I'm glad you watched this video. I hope that you have found it informative, and if at all possible, leaving some feedback in the comments section would help me create much better videos for you in the future. Thank you for watching. Have a pleasant day.